Okay, then, so one often comes across a very interesting case where you have to do an integral of a function which has a singularity on the real axis, okay? And a lot of times you have to, take contours which go like this. You have to go like that, and then you have to go around this, and then you have to go like this, and this is some epsilon radius, and then epsilon has to go to 0. Okay, so so there's a theorem for such contours, and these contours are actually very useful in physics. These contours crop up because when you're solving linear differential equations, when you're trying to figure out what are known as propagators, you have to do this sort of integrals all the time. And so for this sort of things, this looks like a mouse hole, right? It's like from Tom and Jerry. So this theorem is called the Mousehole contour theorem. Okay, these kind of contours are called Mousehole contours. So Mousehole contours, the contours that we looked at before, we took the limit going to infinity. Here, the limit would be going to 0. And so, what are Mousehole contours? So suppose that we have some axis or some line, and we have on that some point over here. This is a simple pole of, say, f of z. So this is a simple pole of the function f of z. And suppose that we are now looking at a contour which comes like this, and goes like this. Sorry. Okay. So this angle is, say, beta, and this angle, suppose, is alpha. Okay. So this contour, the little, and this is epsilon, this radius. Okay. So now, and this doesn't have to be at 0. Suppose this is at, the real value of this point is a. So we can the curved part of the contour, we can call it, say, phi of epsilon, and this will be given by a plus epsilon e I t. Okay, t is the parameter which goes from alpha to beta, right? Because as t is, when t is alpha, we are here, and as t is increased to beta, we go here. Is that clear? That this formula catches this little part arc. So okay, so then as I take the limit where epsilon goes to 0, let me just keep the picture. And if I integrate my function with a simple pole on this contour, then it's very easy to show that this will be given by beta minus alpha times I sigma. What is sigma? Sigma is defined by this. If you take if you define g of z to be a non-singular function, which is holomorphic at z equals to a, and then you can express f of z to be z minus a. So what are we doing? What we're saying is that we're expanding f of z around the singular point, and the non-singular part of that function we're calling g of z. And the coefficient of the singular part, the residue essentially, is sigma. Okay, so then we can show that this is true. Okay, so this is a very simple result, and you can show this very easily. Okay. And you have to, right. Okay, so this is another theorem. I'm not sure if I want to. Yeah, let's see if we can do an integral. It's a little involved, but yeah, okay. So let's do an example of this. So suppose that we have to do this integral from 0 to infinity of a function which is x minus sine of x. Let me expand this. Divided by x cubed. Now, the problem with this is that at x equals to 0, the numerator is 0, right? But the denominator blows up. Okay, so it's not clear that this is actually something that makes sense as an integral. And of course, this doesn't seem to even fit our description of what we. So okay, but let's just proceed anyway, because this is an even function, right? Because both the numerator and the denominator are odd functions, so the whole thing is an even function. So we can write this as 1 over half. By the way, I've chosen all these examples to be, to be representative of the cases that we're doing, but some of these examples are way too hard. They don't actually have to be, in applications, you might find them to be simpler. So for example, this one has a cubic, a pole of order 3, right? So which is not obviously going to be applicable to the Mousehole contour, but we'll see with a little bit of cleverness, we can sometimes use, this result to more complicated cases, which is why, yeah, okay. So this is going to be half of x minus sine of x by x cubed d of x. Now, consider the function f of z, which is I times z minus e to the power I z divided by z cubed. Okay? Now, if I factor out 1 over z cubed, I get I of z, and then let me just expand this guy. This guy is going to be 1 minus I of z plus z square factorial of 2 dot dot dot. Okay? So then this guy will cancel this guy. Okay? Just 1 second. Right. Okay, so why did we do this? The reason for doing this is the following. This term has 1 over z cubed in it, right? So, if I look at this term itself is a function which has a triple pole at z equals to 0. But this guy multiplying this guy is going to have a simple pole, right? And the imaginary part of this function, so the imaginary part of this function, coincides with our integrand. So now if I define another function, h of z, such that it is our original function, iz minus e to the power iz divided by z cubed plus 1 over z cubed. Hang on, someone wants to come in. Okay. I think they're, okay, they probably joined. Okay, 1 over z cubed. Then we see that this part will cancel this part, and then we'll be left with a simple pole. However, when we added this guy, we actually did not so when we added this guy, we actually did not change the imaginary part of the function on the real line. Okay? Is that clear? So just 1 second, okay? Okay, this is a bit of a complicated example, so let me just explain again, okay? So we chose a function, f of z, now if I evaluate this function on the real line, then I get ix e to the power minus ix by x cubed, right? Do you agree?
Yes, sir.
Okay. But this is a complex function, right? It's a complex function,
yes,
even though the variable x is real. So now if I take the imaginary part of f of x, I get x minus sine of x over x cubed. Okay? Is that clear?
yes, sir.
Okay. So what we are interested in is we are interested in the integral over the real line of the imaginary part of this function evaluated on the real line. Okay? Now let's look at another function, 1 over z cubed. Now this function on the real line becomes 1 over x cubed. Okay? Is that clear? On the real line.
Yes, sir.
So does this function have an imaginary part?
No.
No. So if I take my original function f of z and add to it a new function, say 1 over z cubed, am I changing the imaginary part of the original function evaluated on the real line?
No, sir.
Right. So my new function h of z, when I evaluate it on the real line and take its imaginary part, then that will be equal to the imaginary part of the function f evaluated on x, right?
Yes, sir.
Okay. Now look at this nice function h of z. F of z was not a very nice function because it had a triple pole at z equals to 0. But this function, h of z, now doesn't have that triple pole at z equals to 0 because we are subtracting this. Because if I look at f of z and I expand it over here, I've expanded it, see that the triple pole comes with a minus sign. And we have added 1 over z cubed to it. So h of z only has a simple pole at the origin. Okay? Is that clear? H of z
Yes,
has
sir.
a simple pole at the origin, right? The other thing that it has, if I take the integral of the imaginary part of h evaluated on the real line, that will be this equal to minus infinity to plus infinity of the imaginary part of f of x evaluated on the real line, right? Because we have not changed the imaginary part of those functions evaluated on the real line. Is that clear?
Yes, sir.
So, but this is a much more nice function for us to evaluate, and we can now use the Mousehole contour on this guy. Okay, let's look at its contour. So we have a what contour should we use? We have this is this uses a lot of this theorem. So this is my simple pole, and I take this, and I take this. Let me call this, say, C1. This is C2. This is C3. This is epsilon, or let's call it small r. Small r. And then we close this, and this guy is big R, and this is C4. So there are no singularities of that function inside this closed contour. We can express that fact by saying the contour integral over C1 plus the contour integral over C2 plus C3 plus C4 of h of z d of z is 0. Okay? This is Cauchy's integral theorem. And now I take r goes to infinity. And if I take r goes to infinity, if you look at the if you look at my integral separately, then by Jordan's lemma and the other lemma, we see that the contribution from C4 part goes to 0. Okay, it's this part. And if you take r goes to 0, because this guy now has a simple pole, by using the Mousehole contour theorem, where alpha is 0 and beta is pi, so the contribution from that guy is going to be so contribution from this part and this part. So let's write that. C1 h of z d of z plus C2 h of z d of z. That is going to be given by minus C3 h of z d of z. But this thing from the Mousehole contour is going to be pi minus 0 divided by 2 times I. And therefore I have I pi by 2. By 2. Sorry. And this is an imaginary number, but of course we have to take the imaginary part of this integral. Remember that we were interested in the imaginary part of the integral. And therefore, and then divide by half, because our original integral was from 0 to infinity. And then 0 to infinity is going to be x of x minus sine of x divided by x cubed. D of x is pi over 4. Okay. So I think I'm going to end here. There is another fun example involving logarithms, but I think we're going to skip that. And in the next class, we'll go back to physics. And what I'll do is that I'll get some fun contour integrals for you to have a go at for the tutorial, okay? So if you found this lecture to be very technical and a little bit out of your depth, don't worry about it, because you're not going to be examined on it. It's just showing you some fancy tricks about how to use complex analysis to do contour integrals, right? Okay. Do you have any questions?
No, sir.
Sir, is there a book to go through this stuff that we went through this time?
Yeah, as I said earlier in the class, I'm going to upload my lecture notes that I gave at PI. So there'll be a set of 4 lecture notes that I'll upload onto the Vuex. Also, there is a book that I will recommend. Okay.
Okay.
It's a book that you can. It's actually a book that you can read on Mathematica. And I actually have a copy of this, and I can share that with you. I would be violating all kinds of international copyright, but that's okay. I mean, as long as you don't tell on me, it's fine. I use that book most of the time when I use a few other books too, but that's the book that I use the most. Okay, so my advice to you is that if you're doing quantum mechanics, you should be thinking about quantum mechanics and not worry so much about the complex integral stuff, okay? This is a diversion. So one of the worst things that you can do while learning a subject is to actually get diverted and going down a rabbit hole on something else and then losing track of the main topic. And it's helpful, but it's helpful only to a certain extent. Okay, sorry, I lost the. So I wouldn't worry so much about this. Okay.
Okay, sir.
So I know, Shujosh, you have a tendency of going down rabbit holes, so that's why I'm warning you not to do that. Okay, just skim through the lectures that I uploaded and just try to get the general idea. The general idea is that you have, okay, let me just tell you what you need to know. You need to know just this thing, one thing. That when you have to usually do some real integral of some f of x on some minus infinity to plus infinity. And what we will do is that most of the time you will replace this by a complex function f of z. And what you will do is that you will find that this function, has some poles in the upper half plane as well as some poles on the lower half plane. And you will find that, either this upper contour, when you close the upper contour, or the lower contour, that one of them goes to 0 as you take r goes to infinity. Suppose it's the upper one that goes to 0. In that case, what you want to do is that you want to do you want to do this integral f of z, d of z, on some contour where the contour goes from minus infinity to plus infinity and then closes up here. Then this is going to be equal to 2 pi I times the residue of the singularities here. But you see that the contribution from this curved part is going to be 0, because it'll have some exponentially decaying part, or a part which is 1 over x squared, and it's going to go to 0 very rapidly. And therefore, you're left with contribution only from the real part of the integral. And that's how, you can evaluate it, the real part of the integral, just by computing the residues of these poles, okay? So this is the simple conceptual trick. Everything else is technicality. Everything else you can look up in a book or online these days, okay? So do not go down the rabbit hole. Just have an overview of how to do complex integral is in this one slide. Okay?
Okay, sir. Yeah.
Okay, any more questions or comments? I also posted your first assignment today. I only gave it 10 days because I want you to be, it has, I believe, some interesting exercises. Maybe 1 or 2 is a little bit hard, but it's not that hard. So I want you to try it as soon as possible. And in a few days, I will instruct Moon on those examples, so that if you need some help or pointers, she can help you, okay?